So Hamid is originally from Iran, where he studied mining and petroleum engineering, and in France he specialized in georesources at the University of Grenoble-Alpes. I hope I pronounced it correctly. During his PhD here at the Utrecht University, he worked with Professor Oliver Plumpe and became an expert in microstructure characterization and imaging processing using deep learning methods. Exactly the topic we're discussing today, I think. So currently he's doing a postdoc here at Utrecht. We're very happy. He's running the X-ray facilities for the Excite network and collaborating with Excite users to help them get the best imaging results. So if you are planning to apply and want to come here in Utrecht, you can actually see Hamid in real life, which is of course great. So Hamid is very much interested in multimodal machine learning to integrate different sources of data to answer complex questions. I think that's a great way of really harnessing the power of data. And he's also developing a graphical user interface so anybody can do the similar analyses as the ones that he's presenting today in the webinar. So that's also one to look out for. So maybe you can even do these kind of analyses that he's talking about today. So Hamid, please, the floor is yours.
Thank you very much, Celine, for your nice introduction. Let me try and share my slides. Okay, can you see the slides now?
Yeah, perfectly.
Good. So as Celine mentioned, today I'm going to talk about characterizing and reconstructing porosity evolution during fluid rock interaction using 4D synchrotron tomography and generative AI. So I first start with a brief introduction because most of you probably know these things, but as you know, when the minerals are in contact with the fluid that is not in the equilibrium with them, they start to dissolve and release ions like A and B. Get my laser point. Yeah, they start to dissolve and release ion like A and B in the interfacial solution. And then that solution can contain ion C, and if it can reach the supersaturation, it can nucleate and precipitate on the surface of the parent mineral. And then if this dissolution and precipitation continues, it can lead to the replacement of one mineral with another mineral. And this mechanism is known as interface coupled dissolution precipitation, ICDP, which has been extensively studied in the past few decades with some common features like usually we see a sharp interface between parent and product phase, as you can see in this example here. It can also be that the crystallographic information transfer from the parent to the product phases, especially if there's a epitaxial relationship between them. And the last but not least is the generation of the connected porosity in the product, which is the focus of this presentation today. And this porosity generation is an essential part of the ICDP because it provides the pathways for the fluid to stay in contact with the parent mineral and for the replacement to continue. And it depends on several factors, for example, difference in mineral solubility, fluid composition, and changes in the molar volume. For example, if you have a positive change in molar volume, then you will have the porosity in the form of induced fracture. And if you have a negative molar volume, which means that the product phase has less molar volume than the parent phase, then you can generate reaction-induced pores, which is the case in pseudomorphism, for example. But as you can see in this SCM image, these pores, the black pixels, are now disconnected. And this is because that this porosity generation is a transient feature. And what it means is that during the reaction, we have a connected pore network, but the reaction, when this reaction is over, the pores become disconnected due to the precipitation mechanism. And what we want to do, we want to analyze the evolution of this pore space. And for doing that, the first step is to design experiments. So first we can see this process. And to do this, we went to the PSI synchrotron in the Switzerland, and we used the KBr KCl as a salt analog for the natural reaction. So we put the KBr crystal in an X-ray transparent cell, it's called a Stigner cell, and then injected the KCl fluid and did a tomography at every 1 minute at the pixel size of less than 3 micron and at the room temperature. So we did a couple of experiments. In the first experiment, we didn't use the cell, so we just dropped the KCl fluid on top of the sample and did the tomography. And here you can see some snapshots showing the mineral replacement going from top to the bottom of the sample. And in the second experiment that I show you today, we used the X-ray cells. So we put the X-ray KBr crystal in the sample, and then we injected, we applied the small confining pressure of about 10 bar, and then we injected the fluid from bottom of the sample through a small hole in the center of the sample from the bottom that you can see here, and then did the tomography. I can also show you some slices. Here you can see from experiment 1 on the top view, you can see how the pores are generated and how they connect together with time. And if you look at the side view, you can see how the reaction interface moves downward and how these pores are created in the shape of this channel, which serve as an effective pathway that allows the flow to access the reaction interface so that the replacement continue. So we did a couple of experiments and we acquired a large data set, about 10 terabytes of the images that then we segmented using a unit convolutional neural network, which is a supervised learning method, but I'm not going to explain that method in the details. You can find more details in our paper, but I'm going to skip that today and go and tell you how you can characterize the pore network after the segmentation. So by characterization, here we mean statistical quantification of structure and morphology of microstructures using a spatial correlation function, also known as statistical microstructure descriptors, or SMDs. So these SMDs are defined as a probability of n random points with a distance r to lie in the same phase. For example, you can define 2-point correlation, 3-point, 4-point, and so on. So for example, 3-point and 4-point shows the geometrical pattern in your microstructure. But you can also define connectivity descriptors. For example, linear path is the probability of the whole line to lie in the same phase in your pore space. And we also have a 2-point cluster function, which is similar to 2-point correlation function, but here the 2-point should lie in the same connected pores. And if you calculate all this probability at a different r, the different distance, what you get is a plot like this, which shows the probability, and in x-axis you can see the r, the distance between the points. And by using all of these SMDs, you can accurately quantify your microstructure. But another important advantage of these tools is that they are interpretable. For example, at R0, the probability at R0 shows the porosity because the definition reduces to the probability of 1 point, which shows the phase fraction. So in this case, porosity. At the small r's, it gives you information about a small scale feature, for example, the pore size, pore channel size, and so on. And at the larger range, it gives you the information about the longer range correlation in your microstructure. For example, if you have a pattern that is repeated at a specific distance in your image, you will see that as a bump in your SMD curves. So these are the tools that you can use to quantify one image, one snapshot. And to quantify the microstructure evolution, we use a metric, which is called omega metric, and it simply just calculates the L1 distance between the SMDs at time t with respect to the initial at time 0 in the initial curve, for example, at the beginning of your experiment. But it also can be any reference point in your experiment. So here it shows the 2-point correlation, but you can calculate the distance between each curve at each time with respect to the initial curve. Here you can see some results. You see here that in this experiment, in the experiment 1, in the XY plane, you can see at the beginning that all the SMDs rapidly increase at the beginning, but at some point, after about 140 meters, they all stabilizes, except the 2-point cluster function, this purple curve. And this shows that after this time, your microstructure doesn't change that much, but the only thing that is changing is the cluster connectivity between the pores, which increases with some oscillation. And if you look at the XZ plane, the side view, you can see that so it's always 2-point correlation because it's lower order, it has a higher value. But here you can see that the linear path, which shows linear connectivity, this orange curve, shows higher value than other SMDs. So this shows that the linear connectivity is the dominant pattern in this image. You can also calculate and quantify the pore evolution in 3D using 2-point correlation. So here, the black curve shows the evolution of pore, the 2-point correlation, and the blue curve is a normalized version. It's called the F2 autocovariance, it's called. And it's normalized by the total porosity. So it highlights the evolution of the pore structure independent of the porosity. And if you look at it here, you can see again at the beginning, you have a rapid evolution, but then you have a change of behavior and it starts to decrease. And at some point, it stabilizes again. And a similar pattern you can see in the experiment too, except that here it continues to decrease until the end of the experiment when we have a sharp drop in the curves, which shows that it's a big precipitation is happening at the end of this experiment. Another thing you can calculate is the average chord length. So if this is your pores, and if you draw a long line, then the chords are the line segment between the two-phase interface. So the line segment here, you can calculate it in 3D and in average. So it's kind of show you can see it as an estimation of the average pore size or pore throat size. And it can be calculated using the 2-point correlation behavior and like its value and its derivative at the beginning of the SMD gives the 2-point correlation function. And if you look at this, the results of this average correlates, you can see that again at the beginning you have a rapid increase in the average chord length, which is probably because of the creation of the channel-like shape. And then after that, you can see that it still increase gradually, but at a very slower rate. So it shows that shows a pore coarsening happening here when the pores increase in the size and in the pore throat size, for example. And you can see also the similar pattern happens in experiment 2. So these were the SMDs, but another set of tools that you can use is the Minkowski functional. So Minkowski functional are initially introduced in integral geometry and can be used to describe the geometry and topology of the complex material. And for a 3D image, for the 3D volume, you can define 4 Minkowski functional. The first one is volume, shows the volume of the pores. The second one is the surface area. The third one is called integral mean curvature, which shows kind of the bendiness of the pores. For example, if you have a more convex shape of pores, you will see an increase in the mean curvature. And if you have more concave pore, you will see it will decrease the integral mean curvature. And the fourth Minkowski functional is called Euler characteristics, which shows a connectivity of your pores. And if you have the more negative value for Euler characteristics, it shows higher connectivity. Here you can see the result of mean curvature and Euler characteristics. And if you look at especially the Euler characteristics, you can distinguish 3 different stages. So at the beginning of this curve, you can see that the Euler connectivity is about 0. So it means that the pore network is not connected. But at some point, it starts to rapidly decrease towards the negative value. So it means that the connectivity increases significantly. And at the later stage, you can see that it's again a plateau and stabilizes with some oscillation. You see the similar trend in the experiment too as well, except that at the end of the experiment here, again, you see a sharp increase in the Euler connectivity, which shows that the connectivity decreases. And again, this is a hint that shows that you have a large precipitation in the experiment too. So then he also calculated the evolution of the transport properties, porosity and permeability. So here the black curve shows the porosity evolution. As you can see in the experiment one at the beginning, with the small increase in the porosity, you have a several order of magnitudes increase in the permeability, which is shown by this color curves. And in the second stage, and after that, you see that the permeability increases much more slowly, which is probably because of the increase in the connectivity that we saw. And at the later stages also increases, but again more slowly. And this could be related to the pore coarsening that we saw in the average core lengths, for example. You see more or less the similar trend in the experiment too. But if you may notice that here, for example, there's a difference in the experiment. One, you see that the permeability becomes anisotropic. So you see this divergence between the permeability in different orientation. And you see the similar pattern in the experiment too. But at some point in the second stage, you see that the curves start to converge again. And you can see here in that I show you this evolution of the pores in the 3D. So you can see that in the experiment one, you see these channels are created and continue without any big change in their shape, and so they preserve their shape, but the connectivity between them increases at some point. You see the similar thing in the experiment two. You see these channels, but as you will see in a second, the connectivity becomes much higher, so the fluid flow become more isotopic at the end of this experiment because the pore are highly connected at the end. So and that's why you can see this more isotropic at the end of the experiment too. So you saw that with the combination of these SMDs and also the Minkowski functional, they provide a lot of useful insight about the porosity, evolution, its structure, and its morphology. And with that, we could identify three stages. The first stage was a rapid evolution, where the channel shaped pores created, but the connectivity was not high. We had a low connectivity. In the second stage, that we call it the transition stage, we had this pore evolution slowing down, and also we saw an increase in the connectivity. And finally, in the stage 3 steady state, we had this stabilization in the microstructure. The pore remained connected, and we saw also some pore coarsening. So these are the information that you can get with these tools. And then what we did in the second part was to use the data that we acquired during the experiment to train a generative model with two motivations. So the first was that we wanted to see if we can learn this porosity evolution that we observed during the KBR case or experiments, and then to see if we can apply what we learned on the natural sample, for which it's not possible, it's not yet feasible to perform the similar experiment because some system and some replacement require very high temperature, and we don't have, at the moment, we don't have the cell X-ray transparency that can go that high temperature. So basically what we want to do, so you saw this before, pores become disconnected at some point because of the precipitation and so on. And what we want to do with the generative AI, we want to reconnect back these pores to the time of the reaction. So we want to reconstruct the pore connectivity at the time of the reaction. So this reconstruction and image reconstruction, we do it with a generative model. So the core idea in the generative model is that you can sample from a prior distribution, which is usually a normal distribution, and then you map it to the complex distribution of the training data. And if you can learn such a mapping, then you can sample from the normal distribution and generate statistically equivalent and realistic microstructure. And we use the generative adversarial networks, or GAN, for this. So in GAN, you have two convolutional neural network, discriminator and generator, and there's a competition between them. So generator samples the normal distribution and it tries to generate fake image that looks realistic. And then this fake image with the real image goes to the discriminator, which is basically classifier whose task is to distinguish between real and fake image. And then you calculate the loss and you update the parameters until you reach equilibrium, which is the point that your discriminator is no longer able to distinguish between real and fake images. And then when you train a model, you can use the generator to generate with realistic image. But this is not the only thing you can do. So you can generate the image, but also what you can do is semantic image editing. So semantic image editing is a hot topic in the computer vision, and it means that you can edit a real image by manipulating the image attributes in the latent space of the model. So for example, this is a photo of me a few years ago before starting the PhD. And one attribute, for example, here could be age, and you can change that attribute and make me younger or make me older. So this is actually not bad prediction. And also another expression could be, for example, another attribute could be expression. So this is me usually in the morning without the coffee, and this is me after the coffee. So it can change the attributes of your image realistically. So, and these are the attributes in this example. But what we can do is that that attribute in our case could be the pore connectivity. So we want to learn how we can realistically edit the connectivity and connect the isolated pores based on what we have learned from the experiment. So I'm not going to the more details of how you can do this. You can read our preprints, which is in the registration page. If you go, you have the link to the two-part paper, and this generative AI is the second part. You can read. There's a lot of detail on how you can edit the image in the latent space of the generative model. But I want to show you the results and show you how you can use again the SMDs to validate our result. So here you can compare the results of our generative model with the evolution of the real images from the experiment. And as you can see, you'll see a good match between the evolution of the SMDs with the result of our model. So it shows that our model is able to reconstruct and reconnect the pores based on what it has learned from the experiment. And then after this, we try to apply this model on the natural sample. For example, here the natural sample was a meteor-igneous rock from Oslo Rift, showing the feldspar replacement with a sharp interface. And so here you can see, I can show you two examples of how our model can reconnect the isolated pores of the SEM image from this natural example. And then we apply this model on a 3D image, slice by slice. Here you can see how the activity is improving. So here each color shows a one connected pores. And if you then we estimated the permeability using a voxel-based final element method. And here, if you look at the results, you can see that you can have a few order of magnitude increase in the permeability by reconnecting the pores. But the limitation here was that here we cannot do this. We cannot run the similar experiment on this granitic rock sample. So we don't have a real permeability at the time of the reaction to validate the results with that. But what we did, we compared the results with the previous studies. So here shows the permeability versus depth. And the blue curve here is the average permeability over the large scale than over the long time. But there are several methods like using the hydrothermal and the metamorphic model. The several experiment has shown that this curve can shift towards the higher value because of the tectonic or metamorphism transiently. So it shows that in the transient, when the reaction is in effect, you can have a several order of magnitudes increase in the permeability. And knowing that our sample is coming from a depth of around 10 kilometers, if we put the result of permeability, we can see that there's actually a good match between the permeability value we got and this red curve. So with that being said, I would like to continue to conclude with a few takeaways. So we saw that how you can get a lot of insight and information about the microstructures, the structure and the morphology of your images using this SMDs and Minkowski functional. And you can use this to quantify your microstructure, and it's not limited to just the porosity. As long as you have a segmented image, you can apply this method to quantify your images. And if you're interested and you want to use this model in your paper, in your work, you can go to our GitHub page, and there you can find all the codes to do the same analysis. And as Selim mentioned, I started to work on making a user interface for the Excite user, but also for the whole community of geoscientists that can simply apply and quantify the microstructure using these methods. We also saw that the generative model can learn the evolution of the microstructure, and the knowledge that we learn from experiment can be transferred to the natural system. This is also, of course, needs a lot of more experiments to be done on the different system, but that will be something that you can do if you don't have access to the synchrotron, and if you have sample that is you cannot do the one experiment, you can use these models from the other experiments to apply on your image of your sample. And with that being said, I would like to thank you very much for your attention. I would be happy to answer your question.
Thank you, Hamed. I thought it was very interesting to see all of this happening, and that actually an AI model can come so close to the real deal. So that's great. So if you have questions, I see that that we are a little bit over time, but it was just so interesting, Hamed. So thank you, thank you very much. So if you have time to ask us any questions, please do. You can put them either in the chat or the Q&A, and I can ask the question for you. Or you can raise your hand and I will give you the floor. So I will then also spotlight you in that sense. It sounds very interesting, but maybe not. It's not that interesting. Okay, so I have a question here. So so how transferable is this workflow actually to industrial or field scale data? So would it be workable?
So what I have done and what you saw in this presentation is in the smaller scale, is in the pore scale. But and the common way to apply this in the larger scale, like a field scale, is to upscaling. So what the people do is that they run the simulation on a smaller scale and then upscale and use the effective parameters, for example, the effective permeability, and use that in a Darcy law, for example, to simulate in the larger scale. And so we are in the pore scales, but what our study suggests is that a lot of complex things happening in the pore scales, and the pore structure and morphology is changing, and the relationship with this with the effective permeability, for example, is complex and changes with time. So one issue in the upscaling is that, for example, there's a lot of relationship between the permeability and porosity or tortuosity and so on. So they use those empirical relationship to update the permeability to run the simulation on continuum and macro scale, but they usually get a lot of, and those relationships usually have like a fitting parameters, and the fitting parameters has a wide range. For example, I've seen from 5 to the 75 values for the different under different specific system and under specific circumstances. So it means that the porosity, the only porosity itself, is not enough to update the permeability in the reactive modeling. But our studies suggest that maybe if we can apply this and use this Minkowski function and SMDs into the model and incorporate them into the modeling, it probably can improve the predictive ability of those reactive modeling in the larger scales.
So you add more parameters, physical parameters that are known of a sample.
Yeah, the parameter that is not usually considered. So what is considered is usually just total porosity, but the structure and morphology of these pores is not usually considered in the most of the studies that I've seen, at least.
Yeah. Okay. Well, good that it can translate. So I've got a question here. So what is the timeline of one experiment in the beamline? So what is the length of a single CT? I think
in terms of time,
how long
so
you measure, or yeah.
So
Sorry.
each experiment, so we did a couple of experiments. So we spent like around 5 days in the PSI synchrotron, and so some experiment failed, but each experiment took about 3 hours. So between 2.5 to 3 hours, we did each experiment until so we waited for the full complete replacement of the KBR by KCA.
Okay.
And the question, but about timing is like 3 hours. But the time between, if they mean that the time resolution, so the time between each scan, it was about 1 minute. So every 1 minute, we took a 3D volume image.
Okay, clear. So what I've got a question here as well. So what are the biggest challenges in coupling these physical principles with machine learning in fluid rock interactions, or maybe also other applications if you
so the machine learning and the deep learning has been considered for years as like a black box that you just put your input and output images, and you kind of learn a relationship between them, or just kind of the mapping from one space to another space. So it's been hard to explain the physics and include the physics, but in the past few years, there's been a new branch in the machine learning, which is called physics-informed machine learning, or physics-informed neural network, where you can add your physical law, for example, your conservation of the mass, energy, and so on, as a part of the loss function. So one good thing with the machine learning is deep learning is that you can calculate and you can compute the partial differential equation very efficiently using the automatic differentiation that you can do with machine learning. So there's been a new way and a lot of ways to incorporate the physics, and that can help to generalize the model better. And you also will need less data because you have some invariant, you have some physics that should be met. But the biggest challenge in our case, in geoscience in general, and also in the fluid rock interaction, I think it will be that we have a multiple physics to include. So we have a chemistry, we have a fluid flow, but you can also deform your sample, and you have like mechanics involved in the sample. So I think that will be the most challenging part, to incorporate all this physics in your neural network, and also need the data of each that shows each physics to be all involved and include in your machine learning. So I think that will be very challenging in the next few couple of years.
So there's a lot to do still on that area. So will it also be included in your kind of approach, the thing that you're developing, this graphical user interface, or is that not a part of the development?
So the user interface is going to be the first version. It's going to be just to calculate these statistical microstructures and Minkowski functional. So it's going to be a very simple thing, but makes this calculation for people that are not familiar with the Python and just want to do this analysis. They can just upload your image and do this calculation and get those, for example, the SND curves. But maybe in the future, we can also, if we have time and we have a project, we can also work on training and make this generative model available for the similar things, for the similar project.
Fantastic. Thank you, Hamed. I think that's a great goal to work on. So with that, I will leave you. Thank you very much for being here today, visiting this webinar, and also for your questions. You will get an email after with a link to watch it back and relive this webinar, but also other webinars as well can be found on the website. And there will also be in the email there will also be a link to a survey. So please, if you find the time, please let us know what you thought of this webinar or of the other webinars that you visited. And with that, I say have a great day and thank you.
Thank you very much. Have a good day. Bye.